Israel has developed a weapon that costs $1 to fire and has an endless supply of ammunition. In a world where we sometimes have to spend tens of thousands of dollars to intercept a single incoming missile, what happens when a country develops a weapon that costs about $1 per shot and has no limit on how many times it can be fired in a day? This is no longer a hypothetical question. Israel has brought a high-energy laser air defense system into active operational use, and its implications extend far beyond a single piece of new equipment. This system appears poised to quietly dismantle the entire economic logic that has fueled drone and rocket warfare in the Middle East over the past decade. However, it also has a very clear and concrete weakness that no one eager to label it a game-changing miracle weapon wants to mention. Please keep listening, because understanding exactly how this weapon works and exactly where it fails will tell you almost everything about the direction this regional conflict will take from here on out. Before we begin, don't forget to subscribe to the channel and turn on notifications. Here is Israel's new miracle weapon. There is a number that has been quietly driving the entire logic of modern warfare in the Middle East for the better part of a decade. And almost nobody outside of defense procurement circles ever talks about it directly. It is the cost-exchange ratio. It is the simple, brutal arithmetic of how much it costs to attack versus how much it costs to defend. And for years, that arithmetic has been getting worse for the side doing the defending, not better. Israel just deployed a weapon that is designed specifically to break that arithmetic. Whether it actually succeeds and what it means if it does is what we're going to walk through completely. Let's start with the problem this weapon exists to solve, because you cannot understand why Iron Beam matters until you understand exactly what it's replacing and why that replacement was necessary. For years, when a rocket, a mortar shell, or an inexpensive drone was launched toward an Israeli population center, the response was an interceptor missile from the Iron Dome system, or in some cases from David's sling or the Arrow system for longer range and more sophisticated threats. Those interceptor missiles work. They have an extremely high documented success rate against the threats they're designed to stop. But here's the part nobody likes to say out loud in public defense briefings. Each of those interceptors costs tens of thousands of dollars. Some estimates for Iron Dome's Tamir interceptor put the cost in the range of $40,000 to $50,000 per missile. And that number climbs sharply for the more advanced interceptor systems designed to handle longer range or more sophisticated threats. Now compare that to what's being fired at Israel in return. A basic improvised rocket built by a non-state actor can cost a few $100s. A small attack drone, the kind increasingly used in coordinated swarms across multiple fronts, can cost anywhere from a few $100 to a few $1,000, depending on its sophistication. The math here is not subtle. If your adversary can force you to expend a $40,000 interceptor against a $500 drone and can do that dozens or hundreds of times, they don't need to win a single engagement. They just need to keep making you spend money and materiel faster than you can replace it. That is the actual strategic logic behind saturation attacks and drone swarm tactics, and it is a strategy explicitly built around exploiting exactly this cost asymmetry. This is not a new observation inside defense planning circles, and it's worth understanding just how long this specific vulnerability has been recognized as a structural problem rather than a temporary inconvenience. Military planners and defense economists have been publicly flagging this exact cost-exchange ratio as unsustainable for well over a decade, going back to early assessments of Iron Dome's own operational economics shortly after its initial deployment. The system worked extraordinarily well at what it was designed to do, intercepting short-range rockets before they could strike population centers. But the underlying financial model behind it was never actually designed to survive a truly prolonged, high-volume, multi-front campaign specifically engineered to maximize interceptor consumption. Every conflict since has effectively been a live fire stress test of exactly how much strain that model can absorb before something has to change. And here's the part that makes this more than just an economic inconvenience. Interceptor missiles are not something you can simply manufacture more of overnight. They require specialized production lines, specific components that sometimes face their own supply chain bottlenecks, and extensive quality control processes. During periods of sustained conflict, when interceptor consumption spikes dramatically, the actual physical stockpile of available interceptors becomes a hard constraint on how long a defensive system can keep operating at full capacity. You cannot print more interceptors the way you can authorize more spending. There is a real physical ceiling on how many are available at any given moment, and that ceiling matters enormously when you're facing a sustained multi-front campaign designed specifically to test it. This is the problem that has been quietly shaping military planning across the region for years. And it's the exact problem that a laser weapon is designed to solve, because a laser weapon breaks almost every assumption embedded in that cost equation. So let's talk about how iron beam actually works, because the physics here matter enormously for understanding both its power and its limitations. Iron beam is what's known as a high-energy laser weapon, operating in what defense analysts generally describe as the 100-kilowatt class. To put that in perspective, a laser in that power range is capable of delivering enough concentrated energy onto a small, fast-moving target to cause structural failure or detonate its warhead within a matter of seconds of sustained contact. The system works by directing an intensely focused beam of coherent light onto a specific point on an incoming target and holding that beam steady on that exact point long enough for the concentrated thermal energy to cause the target to fail structurally, whether that means burning through the drone's fuselage, disabling its guidance electronics, or triggering the explosive payload in a rocket or mortar shell before it can complete its flight path. Here's where things get genuinely fascinating from a technical standpoint. The system doesn't fire a single brief pulse the way a camera flash works. It maintains a continuous beam locked onto the target through advanced tracking optics, essentially holding a spot of concentrated energy on one location on the target's surface, while both the weapon platform and the target itself may be moving. This requires extraordinarily precise targeting systems, capable of compensating in real time for atmospheric distortion, target maneuvering, and the weapon platform's own micro-vibrations, all while maintaining beam accuracy down to a level measured in centimeters at operational ranges. That level of precision is what allows the system to reliably hit small, fast, low-radar cross-section targets like drones and rockets that would be extraordinarily difficult to engage with older generation weapon systems relying on physical projectiles. But the real question everyone eventually asks about laser weapons is this: how is this actually cheaper than firing a missile? And the answer comes down to what the weapon actually consumes to operate. A laser weapon doesn't have a magazine in the traditional sense. It doesn't carry a limited number of physical interceptors that get used up and need to be manufactured, transported, and reloaded. What it consumes is electrical power. As long as the system has access to sufficient electricity and the necessary cooling systems remain functional, it can fire again, and again, and again, with no meaningful limit beyond the power supply and the thermal management of the system itself. This is what people mean when they say iron beam has an effectively unlimited magazine. The marginal cost of firing the laser one more time is essentially the cost of the electricity consumed during that engagement, which various estimates place in the range of a few dollars, or even under $1 per shot, depending on the specific engagement duration and power draw. Compare that to $40,000 or $50,000 for a single interceptor missile, and you start to understand why defense planners have been pursuing directed energy weapons for literally decades, even before the technology matured enough to make them operationally viable. And that's where this story changes, because the speed dimension matters just as much as the cost dimension, and it changes the tactical calculus in a way that's easy to underestimate. A laser weapon engages its target at the literal speed of light. There is no flight time to calculate, no interceptor that has to physically travel through the air toward its target, while the target continues moving and potentially maneuvering. The moment the beam is directed at the target and holds its lock, the engagement has effectively already begun. This matters enormously against very short-range, very short warning time threats, where every second of flight time an interceptor missile requires is a second during which the incoming threat gets closer to whatever it's targeting. Against short-range rockets and mortars fired from just a few kilometers away, that flight time differential between a physical interceptor and a laser can be the difference between a successful intercept and a threat that reaches its target. But here is the part that the more breathless online coverage of this weapon consistently leaves out, and it's genuinely important for understanding what this system can and cannot do. Lasers are fundamentally limited by atmospheric conditions in ways that physical interceptor missiles simply are not. Cloud cover, heavy rain, dense fog, and even significant dust or sand in the air, which is not exactly a rare occurrence in the operational environment Iron Beam is deployed in, all scatter and absorb a portion of the laser's energy before it ever reaches its target. This is not an engineering problem that better software or more powerful lasers can simply solve away. It is a fundamental property of how light interacts with particles suspended in the atmosphere. The denser the atmospheric interference, the more the beam's effective energy is degraded by the time it reaches its target, which either extends the time required to achieve a kill or, in sufficiently poor conditions, can reduce the weapon's effective range and lethality to the point where it may not reliably neutralize a target at all. This is the real question that determines how transformative this weapon actually turns out to be in practice rather than in theory. Under clear conditions, which are common in the region for large stretches of the year, Iron Beam should perform extremely well against short-range threats. But no military planner serious about this technology is going to assume it can fully replace missile-based interception in all weather conditions. What this almost certainly means in practice is that Iron Beam becomes one additional layer in a multi-layered air defense architecture, handling a significant share of the short-range, high-volume threat load under favorable conditions, while missile-based systems like Iron Dome remain necessary for adverse weather, longer ranges, and more sophisticated threats that require different intercept characteristics entirely. There's also a range limitation worth understanding clearly. Laser weapons in this power class are generally most effective against relatively short-range threats, in the range of a few kilometers, rather than the tens or hundreds of kilometers that missile-based systems like David's Sling or the Arrow Interceptor are designed to handle. This isn't a flaw in the specific engineering of Iron Beam. It reflects the basic physics of beam divergence and atmospheric attenuation over distance. The longer a laser beam has to travel through the atmosphere, the more it spreads and the more energy it loses along the way, which means the concentrated intensity needed to actually damage a target decreases as range increases. This is why Iron Beam is specifically designed and deployed as a short-range, high-volume defense layer, rather than a replacement for the entire multi-tiered air defense system Israel has built over the past 2 decades. Now let's zoom out from the technical details and talk about what this actually means strategically, because this is where things become far more complicated than a simple story about a new weapon system. For years, Iran's regional strategy has relied heavily on what military analysts describe as asymmetric saturation, the deliberate use of large numbers of relatively cheap drones and rockets distributed across multiple proxy forces and multiple simultaneous launch points, specifically designed to overwhelm and exhaust a defender's interceptor stockpile faster than it can be replenished. This strategy doesn't require any single weapon to be particularly sophisticated. It requires volume, coordination across multiple fronts, and patience. The theory behind it is straightforward. Even a highly effective missile defense system has a finite number of interceptors and a finite production capacity to replace them. So a sufficiently large and sustained wave of low-cost threats will eventually either exhaust the defender's stockpile or force painful strategic choices about which threats get intercepted and which don't. Iron Beam is a direct, purpose-built countermeasure to exactly that strategy. If a significant share of incoming short-range threats, drones and rockets and mortars can be intercepted by a system that essentially never runs out of ammunition and costs almost nothing per engagement, the entire economic logic of saturation attacks collapses. You can no longer force your adversary into a war of attrition over interceptor stockpiles if their primary short-range defense layer doesn't have a stockpile to attrit in the first place. This is precisely why this specific technology, more than almost any other single defense system fielded in the region in recent years, has the potential to genuinely reshape the calculations behind how conflicts in this theater are planned and executed. But here's what's genuinely important to understand, and it's the part most coverage of this system gets wrong in one direction or another. This does not mean drone and rocket attacks against Israel simply stop being a viable tactic overnight. It means the tactical calculation shifts. Attackers will likely adapt by increasing the sophistication of their approach vectors, attempting to exploit exactly the weather-dependent limitations we just discussed, timing attacks for conditions of poor visibility or adverse weather when the laser's effectiveness is degraded, or shifting toward longer-range threats that fall outside the laser's effective engagement envelope and require missile-based interception instead. Adaptation in military conflict rarely stops simply because one specific vulnerability has been addressed. It shifts toward whatever vulnerability remains. This is the part that matters most for understanding the next 12 to 24 months. Iran and its regional partners are not going to simply abandon drone and rocket-based strategies because Israel has fielded a laser weapon. What is far more likely is a period of tactical adaptation, where attack patterns shift specifically to probe and exploit the boundaries of the new system's operational envelope, testing exactly how it performs in various weather conditions, at various ranges, and against various types and numbers of simultaneous threats. This adaptation process is exactly what you would expect to see in any action-reaction dynamic between offensive and defensive military technology, and it's exactly what happened historically with Iron Dome itself in the years after its initial deployment. Now let's talk about the broader regional and geopolitical dimension of this, because a system like this doesn't exist in isolation from the wider balance of power in the Middle East. Israel fielding an operational, combat-proven directed energy weapon system represents a meaningful consolidation of technological advantage at a moment when the broader regional military balance has been shifting in complicated and sometimes contradictory directions. Iran has spent years investing heavily in asymmetric capabilities, specifically because direct conventional military parity with Israel and its most capable regional partners has never been realistically achievable. Drone swarms, proliferated rocket arsenals distributed across multiple proxy forces, and coordinated multi-front harassment tactics have functioned as a substitute for conventional military strength precisely because they exploit a cost and logistics asymmetry that traditional defense architecture struggled to fully neutralize. A working, scalable directed energy defense system directly undermines the strategic value of that entire approach. If the primary tool used to offset conventional military disadvantage becomes significantly less effective, the strategic calculus shifts in ways that extend well beyond just this specific weapon system. It raises real questions about the long-term viability of asymmetric drone and rocket-centric strategies as a primary tool of regional deterrence and coercion for any actor that doesn't have its own answer to directed energy defense. And that raises an important question worth thinking through carefully. What happens to deterrence when the cost of defense drops dramatically relative to the cost of attack? There's a compelling argument that when defense becomes cheap and effective, the incentive to attack in the first place should decrease, because the expected payoff from launching an attack that's very likely to be intercepted anyway declines substantially. But there's a more complicated counter-argument worth sitting with as well. If a defender feels genuinely confident that a new technology has fundamentally neutralized a category of threat, that confidence could, in theory, create space for a more assertive posture in other areas of conflict, on the theory that a major source of retaliatory risk has been significantly reduced. Which direction this actually moves in practice will depend heavily on how the technology performs under real, sustained operational conditions over an extended period, not just in isolated engagements or limited demonstrations. This is also where the broader regional and global defense industry implications come into focus, because Israel is not the only country that has been investing in directed energy weapons research. The United States, several European countries, and other major military powers have parallel high-energy laser programs in various stages of development and testing. An operationally proven, combat-tested laser air defense system changes the competitive landscape for defense exporters and shifts the technological baseline that other countries will feel pressured to match or exceed. Countries currently investing heavily in drone swarm and cruise missile saturation strategies on the assumption that missile-based defense economics would always favor the attacker over time may need to substantially reconsider that underlying assumption if directed energy defense proves durable and scalable across different operational theaters and conditions. There's also a proliferation question worth raising honestly, even though it's speculative at this stage rather than something we can state as established fact. If directed energy air defense proves both effective and exportable, it could eventually become available to other states in the region, which would meaningfully alter the broader military balance beyond just the specific Israel-Iran dynamic that's driving most current coverage of this system. Whether and how quickly that kind of proliferation actually happens will depend on export control decisions, the pace of further cost reduction and miniaturization, and how comfortable exporting countries are with allowing sensitive directed energy technology to spread more broadly across an already volatile region. It's also worth thinking through what this means for Israel's existing regional security relationships, particularly the security cooperation frameworks that have developed with certain Gulf states in recent years, largely organized around a shared concern about Iranian drone and missile capability. A demonstrated, combat-proven, directed energy defense capability strengthens Israel's position as the preferred technology and security partner within those relationships, and it's reasonable to expect discussion, even if much of it happens quietly and outside public view, about whether and how elements of this capability might eventually be shared, licensed, or co-developed with regional partners who share the same basic strategic problem of defending against low-cost drone and rocket saturation. Whether that kind of technology sharing actually happens, and on what timeline, will depend heavily on classification decisions and the broader trajectory of regional diplomatic relationships, which remain fluid enough that any specific prediction here would be premature. So, where does this actually leave us as of right now, and what should you actually be watching for going forward? The technology itself represents a genuine and significant shift in the underlying economics of short-range air and missile defense. The fundamental claim that a system consuming primarily electricity rather than expensive interceptor missiles could dramatically alter the cost-exchange ratio that has shaped asymmetric warfare in this region for well over a decade is not hype. It reflects real, well-understood physics and a real, achievable engineering accomplishment. But the equally important and often overlooked claim that this technology has clear and physically fundamental limitations tied to weather, atmospheric conditions, and engagement range is just as real and just as important to understand if you want an accurate picture, rather than either uncritical hype or dismissive skepticism. What happens next matters even more than what has already happened, because the real test of this technology isn't a demonstration or an initial period of successful engagements. It's sustained performance across an extended operational period against an adaptive adversary that will inevitably adjust tactics specifically to probe for and exploit whatever weaknesses the system has. Watch for reporting on how the system performs specifically during adverse weather conditions and against larger, more coordinated swarm attacks designed to test its sustained engagement capacity under real combat load, since either of those two currently constitute the honest physics-based limits of what this technology can reliably deliver right now. Watch for how quickly and in what specific direction attack tactics from Iran and its regional partners adapt in response, because that adaptation, more than any single technical specification, will tell you how genuinely transformative this system turns out to be in actual practice, rather than in initial demonstrations and promotional material. And watch for whether and how quickly other regional and global powers move to either acquire similar capability for themselves or develop specific countermeasures designed to defeat or degrade directed energy defense systems like this one. The broader story here isn't really about one specific weapon system, as remarkable as the underlying engineering genuinely is. It's about a fundamental shift in the economics that have shaped an entire category of modern regional conflict, and the accompanying uncertainty about who actually benefits most once that underlying economic logic changes. Cheap, distributed asymmetric warfare has been the dominant model for non-state and semi-state actors, challenging conventionally stronger states for the better part of 2 decades now, precisely because it consistently made a conventionally superior military spend disproportionately more than its attacker in every single individual engagement. A weapon that breaks that specific economic logic doesn't just change one battlefield. It has the potential to reshape the strategic incentives driving an entire regional pattern of conflict that has persisted for years, without any state actor finding a comprehensive answer to it until now. Whether Iron Beam actually delivers on that broader potential, or whether its very real physical limitations end up constraining it to a genuinely useful but ultimately supplementary role within a broader existing multi-layered defense architecture, is a question that the next year of sustained real-world operational deployment is going to answer far more definitively and far more honestly than any single announcement, demonstration, or piece of promotional material possibly could. Drop a comment and tell us where you're watching from, and tell us what you think this actually means for the broader regional balance of power over the next few years. Whether you think this fundamentally changes the calculus for Iran's drone and rocket-based strategy, or whether you think adaptation on the other side will simply route around this specific vulnerability the way military technology development always eventually does when a new defensive capability emerges. That question, more than any single technical specification we've covered today, is the one that will actually determine how this story unfolds. If you're not subscribed yet, this is the moment. Hit the bell, because this technology is moving from limited testing into wider operational deployment quickly, and we will be here covering every stage of it as new information becomes available.